Choosing the right data protection strategies for your Ceph deployments. I'm Anthony Daughtry. I lived in Seattle for 21 years. I'm in the Pittsburgh area now. I've been with IBM for about 6 months now, doing Ceph support for our customers. Also very active in the community. I do huge amounts of upstream documentation work. I help people on the Ceph users mailing list. I administer it. Ceph ambassador, Dan pointed out the community. Well, I wrote a book on Ceph, and in the book I wrote that the community is one of the core components of Ceph in addition to all the software, because it is true compared to any other software I've worked with. And the community is, companies and individuals. It's all a community. Okay, and so this presentation grew out of request Slack conversation with one of my colleagues at IBM, discussing, for a bid, discussing replication versus erasure coding, et cetera. And he was like, you should write a blog article about this. So, I'm going to put this up on the IBM blog later. But so choosing the right data protection strategies for your Ceph deployments. Choosing data protection strategy can be complicated. You have a lot of factors to consider, including, you solve for the usable to raw capacity ratio. Do you want to use replication or EC? What kind of EC? It's kind of a, so many possibilities. There are lots of ways to shoot yourself in the foot, but that also brings with you the flexibility to do what you need to solve for what you need to do. And you could get really deep into this, but we don't have much time, so I'm going to just touch on a lot of these things briefly. Performance, recovery performance, which a lot of people don't think about. Failure domains, fault tolerance, the media, min, Alex size, and IU with new QLC SSDs. At a high level, replication versus erasure coding. Replication, like classic RAID 1, RAID 10, you just have completely separate copies of the data, usually 3. If your data is not crucial to you, you can do 1 or 2. Just you realize that you will eventually lose data, so you want to do at least 3. Most people do 3. In erasure coding, think of it as like RAID 6 or RAID 60. That's the best analog for wider known terms, but it's way more flexible. And the idea is that you split, your incoming data into chunks, and then you make some additional parity chunks, coding chunks, so that you can lose some of them and be able to reconstruct. And the appeal is, depending how you're doing it, you can either survive more failures than replication, or you can get a lot more usable capacity out of your raw capacity. And this is all about the choice of what you're solving for. And when people ask me, well, what should I do? It's, we'll talk about, some things enforce that you need to do replication, but in most cases, it's what you're solving for. The cost, and then Ceph can do whatever you need it to do. Replication, fast and simple. You only have to have, ideally as many as 3 nodes or racks. There's certain advantages to going to more, but you can do it with 3 nodes. High space amplification. And space amplification is what we mean of, the raw capacity, the underlying drives that you have versus what the users can actually use. We call that space amp, to sound like cool storage dudes. So default 3 copies means our space amp factor is 3, 3 to 1. Other values are 1 or 2 if, and sometimes people have data they can regenerate. Sometimes it's a scratch pad. Sometimes it's just data they pull in temporarily to process, to distill, and then throw away, and they keep the important stuff. So, there are legitimate cases for 1 and 2, but if you don't know what they are, don't. And we have a thing called stretch mode clusters, where you can have a cluster over multiple data centers, and there, you need 4. If you have 2 data centers, you need to have 4 copies to ensure high breaking and high availability.
Anthony,
Yes. Oh, sorry.
what good do the copies do if somebody writes malicious software that just goes and deletes all your copies?
That's the thing. RAID is not backup. And this is the same on your desktop too. If you buy one of those cute little drives, USB drives that you plug in, have the really bad power supplies that will fry your drives. put it next to your computer, that's a copy of your data. That's not a backup. Because, if you overwrite, unless you have time machine or something, but then, what happens when, when the landfill area down here liquefies, that's why we took down the 99 overpass, right? And, your house, crumbles in an earthquake. That you can't recover, a backup has to be somewhere else. But,
Yeah, I understand.
okay, happy to talk to you about this more later, but briefly, you can solve that with Ceph. When you do object storage, there's a thing called an archive zone, where you can put immutable copies of your data that can't be deleted. So every time you update the object, the new copy goes there forever. And this, this is the poster child for ransomware. The infrastructure you cannot tell it to delete the data. So you can, built-in disaster recovery.
Okay.
And of course, ideally, if you want to, if the orbit of the Apophis asteroid changes and it crashes in, you might want that on a different continent. But that DR is a whole different ballgame, right? Okay, but back to this because we don't have much time here. Erasure coding. You usually need more hosts or racks or however your scale is compared to replication. A company that I once worked for, who were on Dan's slide, but I'm not going to name them. The CIO wanted me to do erasure coding on 3-node clusters that were overseas in unstaffed data centers. I'm like, no, you're high. I mean, he literally was high. It's a scale out thing. You can do it with 3. You could do a 2-1 EC profile, but for various reasons, that's usually a bad idea. If you value your data, and so in most cases you need at least 4, or however many more for whatever kind of a profile you want to do, and so you have less space amps than compared to replication. So for example, the default EC profile, and we'll talk about this a bit later, that I tell people is a 4+2 profile. And with that, you get double the usable storage out of a given amount of raw drives compared to replication. But there are downsides as well. So if you do 4+2, you really need to have at least 6, servers or 6 racks or 6, 6, we call them failure domains, 6 things that can fail, so that you put 1 copy of the data in each of them. Sometimes we need to minimize, the other way of the same equation, the raw capacity for desired usable capacity. I need 3 petabytes of usable capacity. How can I implement that with the least spend on storage? Or, associated, how can we minimize the data center rack units that you need? I worked for Vario NTT for a long time, and literally had to fight to get 1 rack unit, a server this big, in a closet in Sofia, Bulgaria. So some people tell me, I've had an infrastructure VP tell me, our users are irrelevant. No, they're not. Especially, because racks aren't cheap in data centers, and what do you do when you fill your cage up and you need to expand? Then they're not so free anymore. So if you need to solve for that density, if you need to solve for the how much storage you can get per server, especially how much per watt of power, because power and cooling are the same thing. And so these all drive your choices. One of the subtle things, people, one of my missions in life is to convince people that hard drives are a false economy, and they usually are. There's a certain company I can't name who I showed them that not only would they work better for their service, and also that they should use Ceph instead of writing their own, but that using QLC SSDs would cost them 30% less than using hard drives. I used their numbers. There's a SNIA, SNIA, has a TCO calculator. Plug in your numbers, it's fantastic. John Michael Hans wrote it, he's amazing. And so sometimes when people do hard drives, you would need to put more of them out just to have the performance you need because you don't need the capacity, right? And when you do EC, that just kind of magnifies that because your hard drive can only do so many IOPS. And when you put these, you can buy a 30 terabyte now or hard drive. It's the same interface as when they were 3 terabytes, and you have 10 times the data behind it. It's a real narrow funnel. But very subtly, and a lot of people don't realize when they pick EC, is that means slower recovery. Because when something fails, or when you add, because you have to write, like say 6 copies, data to 6 drives instead of to 3 drives, like you would with replication, and those drives only have, 100 IOPS or something each. All of a sudden, you're giving them double the load, and those hard drives will saturate real fast. So that's one of the downsides of ECs. It's all what you're solving for. If you don't care about performance, but if you have a cluster, if you have a server that has 90 30 terabyte hard drives on it, and you lose one of those, how long does it take you to recover? It's going to take you probably at least a month, during which time you have increased risk of overlapping failures. So this is all part of the equation of what you're solving for. And thus, because of this more writes, depending on your workload, you may actually burn your SSDs a little faster. But this is mostly fear, uncertainty, and doubt, because most enterprise SSDs, 99% of enterprise SSDs never use more than 15% of the rated endurance. So if somebody tells you, oh, we need mixed-use SSDs, no. I spent a year working for Solidigm, the people that make the things. A mixed-use SSD is the same hardware as the read-intensive SSD. It just has more over-provisioning, more spare blocks. And you can change that yourself with a tool. Yeah?
Anthony, real quick question for you on the second to last item, slower recovery. So does that mean you have to read the threshold of K blocks to reconstruct a lost N block? Is that what you're getting at there?
Well, you need to have, we'll get to these details in a bit, but you have K plus M shards.
Yeah.
If for the data to be recoverable, you need to have at least any K of them be available.
K, right. Okay.
But what I meant really for slower was just, excuse me, because your recovery writes have to do so many more writes, and subtly, because if you're doing like 4.2 EC, each write has to touch 6 drives, and so that means there's kind of a gridlock, kind of a reservation process there, and so depending on the size of your cluster, and this is stuff you learn the hard way. It can mean you can have less of that going on in parallel because a bigger subset is locked up at a time.
Perfect. Thank you.
Okay. It was Greg Deffenbaugh inspired this from a Slack conversation when the IBM folks, all about these kinds of things. So I mentioned EC profiles, erasure coding, because EC is fewer syllables. The 2 most important attributes, the only ones most people care about, K and M. Why K and M? No idea. I mean, but
Choose K.
hmm?
And choose K.
K constant. I don't know, but M. K is the number of data chunks. So, like if you have when K, say you have a profile K equals 4, you have 1 megabyte of data that you're going to protect. You split that into 4, 256 kbyte chunks. I changed these numbers in midstream. I just wanted to make sure I made it consistent. And M is the number of coding or parity chunks that you do. So, like, if you think of RAID 6, that's like, K is some number and M equals 2. That's RAID 6. But, EC is a lot more flexible than that, but I won't go into those nuances. And critically, these coding chunks are the same size as the data chunks. And so, in this example, we generate 2 coding chunks. It's like XOR or something like that. Chooses a bit more CPU in the replication. Then we generate 2 of those. And so then we have those 4 data chunks, and we generate 2 more. And so the space-time factor is K plus M divided by K. So in this case, that means 1.5 compared to 3. So for So for a given amount of raw storage, you get double the usable storage. And a couple years ago, I went and just put a whole chart of these up in the upstream Ceph documentation, because people keep asking me, what do I choose? And it's like, I just put a big chart in there of which, it looks a lot like that, because that's a screen cap from from the docs, of just showing what those factors are, because people haven't been doing it for 11 years. It's not nearly as distinctive. One important thing is with EC profiles is that you rapidly get into diminishing returns. I love this term. As K increases beyond, say, 6, the incremental space that you get, quickly, declines. But with the wider EC profiles, you need more servers or more racks. You slow down all kinds of things. Scrubs are slow. Everything. It's like a linear cost increase, but logarithmic, asymptotic. Space savings. So like say, look only at the m equals 2 column. Starting at with say k equals 4, m equals 2, then your 1.5 space amp. You go down to k equals 6, m equals 2, you're down to 1.33. That's a healthy difference. But you go, I recently added 20 to there because some customer who I can't name was asking about 22. And then that only gets you from, compared to 8.2 that they're doing now, that only gets you 1.25 to 1.1, but at considerable cost to complexity and ability to recover. And the last thing you want is multiple overwriting. As your recovery time gets longer, your chance of overlapping failures increases dramatically. Dan noted years ago at an OpenStack summit that, with a sufficiently large cluster, get used to having recovery or backfill going on all the time. And so, you really have to factor that in. As I said before, m equals 1. Just don't. Unless you legitimately can lose your data. There are, but most cases, if you have to ask, then you probably can't. And if you do that, even if you don't lose data, that because Ceph is paranoid about strong consistency, right? Just like Dan said. What that means is, and one reason you do redundancy and distributed storage is that so you can take a server down at a time to, replace a DIMM, update the firmware, whatever. But if you have m equals 1, that data will be unavailable until it comes back up. Mm-hmm. And people will do this all the time, and they'll buy the minimum number of servers based on it, and then they have a rude awakening. So, I even I think last week I took m out of 1 out of the Rook documentation just to discourage people from even thinking that it was a thing. And so selecting the value of k. It's a trade-off of the space amp, performance, fault tolerance. Data is preserved if any k data or coding chunks survive. So any of those chunks, whether they're the data ones or the parity ones, that's the whole idea. You can lose, the data is available with Ceph if any k plus 1 of them are online. But your data is recoverable if any k of them survive. So with a 4.2, you can lose any 2 of those drives, failure domains. They can go up in smoke, and you can still get your data back. That's one of the reasons. And so Dan has some very interesting, very secretive results that he's been hatching up about the real actual durability of different erasure coding and so forth that we'll learn about later. But some other people who are solving for being able to survive more faults as opposed to the usable to rock efficiency, or use profiles like 3.3 or 6.3, or even some cases something like 4.8. And those are not nearly as space efficient, but what they do is that they mean that you can lose more drives and still have your data be available and preserved. There are, again, diminishing returns. You could go do a 331 profile, And your data will be there when the only living things on the earth are cockroaches, right? But at what cost? Let's see, do I mention it here? There's a certain computational advantage to choosing values of m and k that have small prime factors. Somebody explored this a while ago on the list. It's very, very subtle. My math degree is only BS, so I couldn't really follow it. But Rhonda knows, she was there. What was I saying?
BS.
I'm good at that. Math. The computational, and so something like a 17.7 profile would be computationally somewhat disadvantaged because those are both primes and relatively large. Where even something like 18.3 would be computationally better. It all has to do with how it calculates all of that parity stuff. And if you really want to know how that happens, go look on the website. Really the key here is how do I choose which one I need? EC is best when you have at least m plus k plus 1 Faraday domains. And Faraday domain means, for smaller clusters, host. It can mean inter-orbital drive, but you don't want to do that if you care about your data. Hosts, or larger ones, racks, or sometimes other things. But hosts or racks are what most of us see. You can do EC on fewer, but it's tricky and it's really easy to shoot yourself in the foot. So if you have to ask, then it's too subtle. Just don't do it because it's too easy to shoot yourself in the foot. You can figure this at pool creation. You can't change between EC and replication on a given pool after the fact. You can move the data, you can make a new pool and move the data, but you can't change your replication pool into an EC pool or an EC pool into a replication pool. And you also can't change your EC profile in place. You can't go from 4.2 to 6.2 in place. You can set the profile on the pool, but it doesn't take effect. That's a very weird subtlety that you have to be aware of. But there are some pools that we use in Ceph that require replication. When you're doing RGW for object storage or CephFS for file storage, their metadata pools have to be replicated. And this is, that's because their data is mostly in what we call OMAPs, which are today they're stored in RocksDB. And for some reason that is incompatible with erasure coding. I'm sure the gentleman at this table, can tell us why it's incompatible. I don't know. I just know that it is. But when you're doing RBD for block storage, they are almost always replicated. Since the Kraken release back in the depths of time, you can use erasure coding for block storage for RBD, but you still have to have an associated smaller metadata pool that's replicated with the actual payload data is EC. And this has a lot higher latency. And it turns out that block storage clients usually care a lot more about operation latency than they do about the cost. When I was at DigitalOcean, we almost changed the block storage service to EC because the product people wanted to be cheaper. And then at the last second, they came and it's like, actually, no, they care more about the rate latency than they do about the cost. And so we didn't. But yeah, I've never seen anybody saying that they're happy with EC RBD performance unless it's for an archival workload. And in fact, IBM only supports doing RBD on EC for explicitly archival workloads, which we actually did at Vultr. When you do if you use the Vultr service and you do a snapshot of your VM, it gets stored off, RBD export gets stored as an RBD volume somewhere. But that's relatively uncommon for RBD. People usually do different things. EC for Ceph and CephFS and RGW data pools, file and object storage. This is really where EC is mostly used. These applications are often much less sensitive to latency than block. They care more about throughput than latency. They tend to be driven by space amp, which in the sense of cost and density over the performance. Is that a question? Oh, okay. Okay. Okay, I think I'm almost done. Throughput can even be higher with EC than with replication in certain scenarios, but don't count on it. You see, you can do both. With both RGW and CephFS, you can have it both ways, where you can store hot data on like a replicated pool, and colder data on an EC pool, which doesn't need the performance as much. Those can even be on like TLC SSDs versus hard drives, or better on the hard drives, QLC SSDs, which are my jam. You can set users and buckets with RGW to automatically go to one or the other. You can do Lewis scripting, as Steve will talk about. I gained a convert there with Lewis scripting for this to override, so you don't have to rely on user behavior, because getting users to user compliance is like herding cats, right? Even if you aren't allergic to them. I have an enhancement request for Ceph to even do this automatically instead of you having to take any steps. Here are just some of the reasons why this can be advantageous for RGW. We're low on times. You talk to me about this or go read it later. Mixed media, as I mentioned, mixing, the faster but more expensive, SSDs for replication or little hot objects, because at DO we found that small hot objects were the death of object storage. And even like the Scality people once told me, small, tiny objects are the death of any object storage, because it's all metadata operations. And so, you can have fast media, you can do inlining, for the bigger things, including, I never make anything up. Pirated TV episodes dubbed into Portuguese. I saw some of those at DO. Those are usually fine on hard drives or slower media. QLC is the future. Don't buy hard drives. They're not cheaper. Here, there's some references. Mark Nelson, who also works at CLISO with Dan, the premier performance person for Ceph, has the spreadsheet that shows you space amplification with certain things that matter if you're using certain exotic SSDs. Here's a link to that table in the upstream documentation. Here's me. Here is a code that this slide profile told me I had to leave in. This was for World Octopus Day that I found this profile for. I could not get the IBM slide profile to even load. So it's like, forget this. I'm going to go to Google Slides. I wrote a book on Google Docs, and pulled this right in there. And may the tentacle be with you.